Good afternoon, everyone. Hope you're having a fantastic day. We're going to be doing a little bit more with implicit differentiation today, mainly applying it to principles we've already learned, such as tangent lines and all that jazz. So, let's go ahead and get started. Example 1, given x cubed plus y cubed is equal to 4xy plus 1, and it wants us to find the equation of the tangent line at the point 2, 1. So they've given us an x and a y. Well, that was nice of them. So we're going to find the derivative, evaluate, that means plug in these numbers into the derivative, and then write the equation. All right? So it's going to be a relatively straightforward task. First, let's find the derivative. So the derivative of x cubed is going to be 3x squared. See if I can get in a little tighter on this. Plus, derivative of y cubed is 3y squared dy dx. And that is going to be equal to the derivative of 4xy. Now this is a chain or a product rule, right? So it's the derivative of 4xy, so it's going to be 4 parentheses, and your x times y. It's going to be first times the derivative of the second plus second times the derivative of the first, so that's 1, right? And then plus the derivative of 1 is 0. Now, keep in mind this 4 here, I'm going to leave it outside the product rule. That just keeps me in check as far as distributing it back into these guys. So it's going to be 3x squared plus 3y squared dy dx, and that's going to be equal to 4x dy dx plus 4y. Simplify a little bit here. I'm going to get my dy dx's over here onto the left, so I've got a 3y squared dy dx minus my 4x dy dx is equal to, let's go ahead and move the 3x squared over, so we'll have 4y minus 3x squared. Solve for dy dx. So we're going to factor it out of, that's not equal to yet. We're going to factor it out of here, and that'll leave us with 3y squared minus 4x is equal to 4y minus 3x squared. And then dy dx is equal to 4y minus 3x squared over 3y squared minus 4x. Okay, now what we're going to do here is use the derivative, which is this guy, and we're going to come up with our slope, because we already have a point, we have an x and a y. So I'm going to plug that into here, and I'm going to figure out my slope. So I'm going to plug in x for x and y for y. Seems pretty straightforward, right? So here's the notation that goes along with this. It's dy dx, and there's this line that goes next to it. That's the evaluated at 2, 1. That means I am plugging in 2 for x and 1 for y. So that's going to be 4 times 1 minus 3 times 2 squared over 3 times 1 squared minus 4 times 2, which is 4 minus 3 times 4 is 12 over 3 minus 8, which is negative 8 over negative 5, which is 8/5. So I've got a slope of 8/5. So pretty easy enough. Y minus y1, which is 1, this comes from my point right up here, 2, 1, is equal to 8/5, my slope, x minus x1. Not too bad, is it? Okay, let's go on to the back. Example 2 says, given y squared equals 4x, find the equation of the tangent line and the normal line at x equals 1. Now, if you ever have an opportunity to do this, I would kind of recommend doing this actually. Let's say that you got the square over here. Let's say you solved for y first before you did anything else. So you'd have y is equal to plus or minus, because you're taking a square root, the square root of 4x, right? So positive and negative, it would look something like this from way back in the pre-cal days. It'd go something like this for your positive square root, something like this for your negative square root. And then say you plug in a 1 for x, the square, say you go to 1, the square root of 1, 4 times 1 is 2, so you have 2 and negative 2. So this is 1 comma 2, 1 comma negative 2. That's just a very quick little graph thing that you're going to do there for this little equation. Okay? So this will kind of give us something to look at when we're trying to come up with the equation of the normal line and the tangent line and all that stuff when x was 1. So I'm going to do a couple of things. The equation of the tangent line, first off, take your derivative. 2y dy dx equals 4. Okay? Solve for dy dx. dy dx equals 4 over 2y. So that'll simplify actually a little bit to 2 over y. So my derivative is 2 over y. There's a fly flying around my desk. I can't get rid of him. So now what we need to do here is use some of the information I gathered from up here. So on the last problem, they gave me the point x and y, but now they only gave me an x. That's why I plugged in a 1 right here to figure out what I would get. So I've actually got two possibilities here. I've got a point 1 comma 2, and I've also got a point 1 comma negative 2. So I've got 2 points I've got to find. I've got 2 tangent lines and 2 normal lines. Well, this just got complicated. So I'm going to do dy dx evaluated at 1 comma 2, and I'm going to do dy dx evaluated at 1 comma negative 2. Now I'm going to do 2 evaluations here. The first one, if you plug in a 1 in for x, well, there is no x. So I'm going to plug in a 2 for y. So it's 2 over 2, which is 1. Down here, plug in a 1 for x. Well, there is no x. So plug in a negative 2 for y. 2 over negative 2, right? It's going to give you negative 1. So my tangent line, there's going to be 2 of them. You've got y minus y1 is equal to the slope x minus x1. You've also got y minus y1, so it's going to be y plus 2 is equal to the slope x minus x1. Normal lines. That's going to be the same values. The only thing that's going to change is that the slope is going to change to the opposite reciprocal. Now this makes it pretty easy because your slope is 1 and negative 1. So this is going to be set up as, instead of a negative 1, you have a positive 1 over 1, which is 1. Not too bad. Okay, so all I did is I took my 1, made it an opposite, negative 1, reciprocal, so 1 over negative 1, which is just negative 1. So that makes it pretty easy for this question anyway. All right, and then it says, where is the tangent line horizontal / vertical? Where is the tangent line? Well, the tangent line is talking about the slope, right? Where is the, or excuse me, not the slope, but the derivative, right? Dy dx. So let's think about this here. For a horizontal slope, you needed it to be equal to 0. You need a slope of 0, which fraction-wise is 0 over something, right? In this case, it's going to be y, right? 0 over y. Okay, so think about this here. What we need is our derivative. We need dy dx to be equal to 0 over y. Whatever the y value is, I don't care. It could be 0 over elephant for all I care. I just need the top to be 0. But my derivative is 2 over y. My derivative is 2 over y. Can I ever have 2 equal 0? Will 2 ever equal 0? No. It's not possible. So what that means, therefore, no horizontal tangents. That means no horizontal tangents. Vertical is a little bit different. Vertical. To make vertical to make vertical lines, you need your slope to be undefined, right? I need an undefined slope, or 1 over 0. So this is kind of like taking your derivative, dy dx, and setting it equal to the top part, whatever it is, the top, over 0. I don't even care what the top is. But I know I'm going to be setting it to 0 on the bottom. So I've got 2y equals something to 0. Well, where does y equal 0? Will y ever equal 0? Let's check. We actually have a variable now. This is possible. So let's go back to our original equation up here. Say we've got 0 squared equals 4x. So solve for x here. Divide by 4, it's 0. So what that means is we have a vertical tangent at x equals 0. Vertical tangent at x equals 0. All right? Again, this is asking us where is it horizontal or vertical. So where, it's wanting an x value. We know that it's vertical when the slope is divided by 0, right? Or undefined. So set your slope to 0, and you know it's when y is 0. So where is y 0? So I'm going to go to my position function, my original, plug a 0 in for y, see where it gives me for x. This is an equal sign right here. Okay? And we get to the last thing here, which is the second derivative. It says dy squared over dx, d squared y over dx squared. Now, let me talk to you really quick about the notation here. You know that your first derivative was d over dx of y, right? We took d over dx, derivative with respect to x, of y, and that gave us dy dx. Well, now we're going to do the same thing. So the second derivative is d dx, but now you're taking the derivative of dy dx. So multiply straight across, you get d times d is d squared over dx dx is dx squared. That's where the notation comes from, right? You're squaring the derivative versus squaring the entire thing. So that's where the second derivative notation comes from. So remember, we said that the first derivative, dy dx, from the top up there, was 2 over y, right? Well, if I want to take the derivative of that, egads, I'm looking at a quotient rule, Instead, I want to make it easier. Let's do 2y to the negative 1 and make it a product rule. How about that? This fly landed on my document camera. It's staring me in the face. I don't like how it looks at me. All right, so the second derivative, d squared y over dx squared. The second derivative, let's look at this guy right here, right? The second derivative is going to be your 2 stays there, and it's drop your negative 1 down, negative 2y to the negative 2 dy dx. So we took the derivative again with respect to x. Okay, so let's simplify this dude a little bit. dx squared is negative 2y to the negative 2, that's negative 2 over y squared, right? And then you got dy dx. Well, hang on a second. Isn't dy dx 2 over y? Since I know dy dx, couldn't I just write 2 over y and get rid of the dy dx? Because that's the goal, right? I need to get rid of this dy dx. I need it to not be here. So why not just call that times 2 over y? So what I'm doing right here is substituting. I'm going to substitute my value for dy dx because I already know it. Fantastic. Let's keep going. d2y over dx2. So negative 2 times 2 is negative 4. Y squared times y cubed. This is the part that's different on this, is you have to substitute your original. But apart from that, it's not too bad. That's a second derivative with implicit differentiation. Have a great one.